5, 6, 7. Untouched by human hands. I should grab one.
What time did you stay in Greg last night? What time were you in Greg last night? Oh my gosh.
All set. Wow, that's hard to believe. We're ahead of time. Okay, any questions from last time? Online, and assuming everybody can hear me. Okay, no question. Some announcements. I've been told that Wednesday we have no classes, but I'm not convinced of that. I need to see it on the university calendar. So one of the students told me we didn't have classes Veterans Day. So Wednesday there may or may not be classes, but I'll post an announcement to make sure after class. And then Thursday review session, I posted an announcement on Canvas about that. And then Friday, exam 2. Exam 2 will cover from acceleration of fluid masses through and including Friday's lecture on momentum. And I see no questions, so we're just going to move forward on something completely different, but it's still fluid mechanics. So we're going to consider having a flat plate sitting in a fluid. And before the flat plate, the fluid is moving in this one-dimensional velocity vector. It's just moving at a constant velocity, capital U, minding its own business. And there is a fundamental fluid principle. It's never theoretically been proven, but it's been empirically measured many, many times. And it's called the no-slip condition. And it's particularly true when you have fluids that wet solid surfaces. That means they would like to stick to a solid surface. And the no-slip condition says that the velocity of the fluid at a boundary has the velocity of the boundary. Very simple statement. No mathematics involved. So the plate's sitting still and the fluid's moving over. At the plate boundary, that fluid molecule will have the velocity of the plate, 0, it's just sitting there. However, because the fluid is above the plate moving, there has to be a transition in velocity from that of the plate. Again, if it's sitting still, that's 0, to whatever that free stream velocity is, capital U. And so instantaneously at the leading edge, you have one fluid molecule at 0 and the other one at capital U. And remember, the change in velocity over distance is the velocity gradient. And that's proportional to shear stresses. As you move further and further down the plate, and there's a handout for today, almost everything that you'll see on a lot of these slides is right from that handout, and it's very, very consistent with what is in your book. So as you move from that leading edge along the plate, you also have molecular momentum movement, Brownian motion. And so what you'll have is the slower molecules down below, and they're moving really slowly, and the ones up above are moving faster. And when they bounce into each other, you have a molecular momentum exchange. The faster ones moving down will speed up the lower ones, and the lower ones moving up will slow down the ones above. And so this zone where the fluid goes from the velocity of the boundary to the free stream grows as you move along the plate. So up above this zone, everything's free stream velocity. The fluid has no idea this boundary is there, but there is this little zone where you have a transition in velocity from the free stream down to the velocity of the plate. And that transition zone is known as the velocity profile. So this is what I've been describing. You have, starting out right here, this velocity profile, and each of these velocities is moving at capital U. And then again, at the leading edge, this no-slip condition takes over. And what you see is the growth of this zone where the velocity is transitioning from U to the velocity of the plate. And in this case, if the plate is fixed, it's at a velocity of 0. And so you can see how this zone, again, is occurring in which U, if this is the x dimension and x equals 0 starting at the leading edge, and y is perpendicular to that direction, then this velocity profile, U, is a function of where you are in space in the y location. So if you're down at this location, you have a smaller value of the velocity than you're up here. Again, this is all because of the fact that you have the no-slip condition. And that is a signal. It's telling the fluid through this zone of transition that, hey, there's a location where there's a boundary. That's all it does. So this is the velocity profile that we've just been discussing. And again, what we're seeing is that as we move in space in the y direction, we're changing the velocity as we move through space. Okay, velocity profile. So this zone where the velocity is changing is known as the boundary layer. Let's go back to the other one. So it's, again, the distance from where you're going from the solid boundary to up above where you're back to the free stream velocity, capital U. We call that the boundary layer. And we live in the boundary layer. And many of what we design occur in boundary layers. So this is actually incredibly important to everything we do in moving fluids around. So for the boundary layer, people, again, have not theoretically come up with the no-slip condition, but they measure it. That's called empirical evidence. So there are empirically measured characteristics of this boundary layer. The boundary layer is a region where the fluid movement is, it can be characterized by pretty structured movement. That is, that the fluid is moving in laminae, sheets almost. That's one type of characteristic. And you saw this in your labs when you had the pipe and you were putting the dye into it. The dye could stay in a nice, have you done that lab yet? Or is that lab 7? Yeah, I think that's 5. So you could see the dye moving in a nice straight structured lamina. The other end of this is where you have completely chaotic movement of the particles. And there is no structure or laminar movement in the particles. And in this case, all the fluid movement we characterize as turbulent. And basically what turbulence is three-dimensional vortices always moving through the fluid. So at one particular point, the velocity could be all over the place and it could have components in all 3 directions. So those are the 2 end members where you have nice structured movement to completely chaotic. And in between is this transition area. And in the transition area, you may have a subregion where you have laminar characteristics, but above that, you have the chaotic movement of particles. So again, what we'll do is we'll call the height of the boundary layer delta. And delta, again, goes from the solid surface to where the free stream velocity is again achieved. Where we're in this transition region, we may have a sublayer, delta prime, where everything is laminar. So in a sketch, and again, this is all in the handout for today. In a sketch, what we see is, again, the plate starts here. Here's the x-axis, and the y-axis is in this direction. And we have the free stream velocity just minding its own business everywhere the velocity is capital U, and then it touches that surface. And that's when the no-slip condition starts, and then everything follows through with that. And so what happens is the boundary layer, or this region, where the velocity is going from the 0 at the plate, the solid surface, to the free stream, this boundary layer distance, again, is delta. And there's a region where it's laminar, and then there's another region where it's all turbulent. So again, out here, these would be, say, average velocities in here. And above this region, we have, again, the free stream. So out here, and to the right, this is where we have chaotic movement of particles, turbulent boundary layer as it's known. To the left, we have a laminar region, and in between, we have a transition. And what's happening in that transition is there's this laminar sublayer. That starts off at the very beginning, or the leftmost portion of this region, the entire boundary layer is laminar. But what happens at the very upper edge is those molecules, when they're moving against the free stream velocity, are becoming unstable, and turbulence initiates there. And then what happens as you move through the transition region towards the turbulent region is this region of turbulence increases at the expense of the laminar sublayer. And ultimately, by the end of the transition region, that laminar sublayer has disappeared completely. This is actually incredibly important. We use this to our advantage in design, and many creatures have adapted. If you believe that the Earth is greater than 4,000 years old, they've adapted their strategies to take advantage of this. For example, why a shark's skin is as rough as it is. It has everything to do with this diagram. So again, the height of the boundary layer is what we call delta. and the height of the laminar sublayer is delta prime. So how do we classify these regions? Well, the laminar region is occurring where what we call the boundary Reynolds number, which I will explain to you, is less than 500,000. And the turbulent region is where the boundary Reynolds number is greater than 10 million, 10 to the 7. Again, this is all based on empirical evidence and measurements. So what we're saying is we're going back to this figure, and for any particular situation, we can calculate where the laminar Reynolds, where the laminar region is when this boundary Reynolds number, and boundary Reynolds number is equal to the velocity times the distance along the plate divided by the kinematic viscosity. In some of your labs, you've had to calculate Reynolds number. The Reynolds number is a force ratio. Even though the numerator and denominator don't look like forces, it's because certain things have been canceled out. But in the numerator, you have inertia, a force due to inertia, and in the denominator, you have viscosity, or the force due to viscosity. The Reynolds number is a dimensionless number. That means that the dimensions on the numerator, velocity times distance, which is length per time times length, or length squared per time, have to be the same dimensions in the denominator. Kinematic viscosity is the dimensions of length squared per time. So we can identify for any situation, obviously, to get that 500,000, you could have different values of U, you could have different values of X, and you could have different values of kinematic viscosity depending on the fluid. So there's an infinite possibility of how to get to 500,000. Likewise, where the turbulent region starts is where the boundary Reynolds number is 10 to the 7th or larger. And again, there are an infinite number of possibilities to get the boundary Reynolds number to be greater than 10 to the 7th. If we're in between those two zones, you would have the transition. So we're getting to this, but if you look at the last page of your handout, the handouts are over there in case you'd like to grab them. On the, sorry, page 6 of your handout, is a large table. And this is often in the third exam, one of the pages that people will use for their crib sheet. But all these equations are in your textbook, guaranteed. So you will see on the left column these variables, delta prime, delta. And the next column is boundary Reynolds number less than 5 times 10 to the 5th. The rightmost column is boundary Reynolds number greater than 10 to the 7th. And the center column is when you're between those two values. You have an equation for each one of these variables depending on what your Reynolds number is, your boundary Reynolds number. Today, we're just going to focus on the second column. We're going to look at the laminar system. Okay? So that's just a teaser. That's where we're headed. So let's get there. For the laminar conditions, the laminar boundary layer, back in actually just before the turn of the 1900s, so in the late 1800s going into the 1900s, there were a number of students at the Swiss Institute. Blasius was a student of some of the fathers and grandfathers of fluid mechanics. In this case, he developed this dimensionless velocity profile. Remember, what the boundary layer is where velocity is changing vertically away from the plate. So if you look at this, you have velocity on the horizontal axis and distance away from the plate on the vertical. But again, Blasius made this into a dimensionless diagram. U over U0 is just U over capital U. So again, that maxes out at 1.0. That's when you're at the very top of the boundary layer, and now you're going into the free stream. So the velocity right at the top of the boundary layer is almost the free stream velocity. And then to make the vertical axis dimensionless, y over x obviously is dimensionless, and to include some of the fluid properties, even though the Reynolds number, the boundary Reynolds number is dimensionless, The vertical axis is a dimensionless number. So this, again, applies for the entire boundary layer for any laminar boundary layer in any situation. And what's nice about this is you'll notice the lower portion is linear. And so from that, we can actually get the slope. And we're really interested in what happens right there, as you'll see. So these are all the variables you really need to worry about. And they're all pretty self-evident. We've already introduced a bunch of them. So the first one is the free stream velocity, capital U. That could be, for example, the velocity of a train moving through a quiescent fluid, air, and you have a relative velocity. That could be the bottom of a barge. That could be a golf ball. All of these are boundary layer features. X is the distance along the plate from the leading edge. X is equal to 0 at the leading edge and continues as you move along the plate. Nu, kinematic viscosity, mu, dynamic viscosity, or typically people just call that viscosity. Remember, mu over density is kinematic viscosity. I'm sure you haven't forgotten that yet. Delta is the height of the full boundary layer. And when we're looking at the laminar zone, it's the entire boundary layer. There is no sublaminar zone in the laminar zone because it's all laminar. REX is the boundary Reynolds number, which I've explained before. REX PECT is UX over nu. And that's also on your handout. It's on that same page 6, on the bottom of page 6. Y is the distance away from the plate, and U, little lowercase u, or U of Y, is the velocity at any depth of distance away from the plate line. So these are all just definitions we're going to be using. And from, again, what Blasius did on the vertical axis, you saw the square root of REX. So again, here's REX, dimensionless. And the height, again, from Blasius, if you look at the full height of the boundary layer, which is at the very right of that figure, I'm just going to go back a little. So if you just study that point, that's where Y is equal to delta. And so from that point, you can determine that the height of the boundary layer is 5x over Rx to the 1/2, just by, again, his dimensionless velocity profile. The other thing you can deduce when you're looking at that linear section very close to the origin, it has a constant slope. Now remember, we had a plot of basically U versus Y. So du dy, when you look at this equation, du dy is the inverse slope. Half a dozen one, 6 of the other. You could look at dy du, but to us, as you recall, du dy has relevance. So again, right from this dimensionless velocity distribution that Blasius had, the laminar velocity distribution, and this is held up for centuries now. Not centuries, century and a half. Since 1900, this stuff has worked. And it's a very good descriptor of what's happening. So again, this is the velocity profile from which all those equations emanated. Why? Because we know the characteristics of this is known. And again, he based this on observations, but then actually theoretically derived it. So what's the importance of the velocity profile? Close to the bed, where the plate is, there's a region where the velocity increases from 0 to a fairly uniform velocity, uniform value. The degree of the velocity change per unit distance is the velocity gradient, du dy, as we indicated before. And yeah, I want to go back to this slide. And I think we're going to see it again, this one. So remember, we start here. And then we move onto the plate. And we're going from the plate velocity to the free stream velocity. That's du. At the very beginning of the plate, it's happening over an incredibly small distance. As we move along the plate, that distance is getting larger and larger. So where is du dy the greatest? Right at the leading edge, and also right along the surface. As you can see, the slope here, let's change colors. The slope here, remember, du dy, the slope closer to the bed is steeper than the slope farther away. Ultimately, and again, a vertical line is a slope of infinity, but we're looking at the inverse slope. So 1 over infinity is 0. So the steepest slope is closest to the bed. I'll zoom ahead this way rather than getting 1,000. Okay. So a long time ago in this very virtual class, we talked about Newton's concepts of what was happening within fluids. And this is the translation of his actual original text of identifying the relationship between velocity profile and resistance to movement. So what Newton hypothesized was, he was hypothesizing laminar flow, where you have one sheet or laminae moving over another, and they're moving at different velocities. And just like when you rub your hands together, you feel the heat occurring. That's due to frictional resistance. That's what's happening here. And so there must be frictional resistance when you have relative motion of these laminae. And what Newton hypothesized was that the magnitude of that resistance, which we call shear stress, is proportional to the gradient, the velocity gradient, du dy. And so what he then theorized that when they're moving at the different velocities, the shear exists between them. And he just said that, well, the shear stress should be proportional to the velocity gradient. And he just wanted, it's really tough to work with proportionalities and equations. So to make that an equation, if you recall, he created this proportionality constant, the viscosity. And that's what we used a long time ago when we were talking about fluid properties. Newton's law of viscosity. Oh, what do you know? I'd already written it there. Okay. So this is Newton's law of viscosity. We recognize from what Blasius did, du dy can be teased out of that dimensionless velocity profile. So this is, and this is on your handout. This is all these notes are in the handout. Du dy from the Blasius velocity profile is 0.332 u to the 3/2 over x to the 1/2. So what we can do is substitute this statement here, and we can solve for anything we want at that point. So in this case, if we solve for the shear stress, and we look at a very particular shear stress, the shear stress right where, that's why this is called tau 0. The shear stress right at the plate. Again, that's where the velocity profile is the steepest, and that's where we'll have the highest shear stress. So this would be an equation describing the shear stress along that plate at any distance x due to a free stream velocity capital U and fluid with viscosity that is buried not only in the Reynolds number, but also appears in this first term, mu. Okay, so that's nice. Again, tau 0 is the shear stress of the plate where y is equal to 0. So the shear stress exists throughout the fluid column, wherever you have the boundary layer. However, the most important shear stress to us is right at the plate boundary. Think of a stream. This is how we determine whether sediments are going to move or not. The stream is creating a shear stress on the bed of the stream, and each particle has a resistance to that movement. And this is what we use to figure out whether you're going to get scour deposition in streams. This is what you use to figure out how many horsepower you need for your boat. It's all due to frictional resistance. So when we look at this, and again, I'm going to remind you, we're looking at the laminar zone only, what Blasius hypothesized. If you look along the plate, so on the horizontal axis, you have the x direction increasing to the right. And so this is the leading edge of the plate. And somewhere down the line is the trailing edge. And what you see is, as we recognize, the shear stress is the largest at the leading edge, because again, you're going from the plate velocity to the free stream velocity over a very small distance. As we move along the plate, du stays the same, plate velocity to free stream velocity, but the distance between them, dy, keeps increasing. And so the shear stress goes down. Likewise, as you go along the plate, the boundary layer is growing. It's growing, it's growing, it's growing. And sometimes what we do in engineering is try to control that boundary layer height. Or more importantly, we may be after trying to control the shear stress. So this was the equation that we derived from looking at Newton's law of viscosity and what Blasius has determined for the dimensionless velocity profile for the laminar zone. And again, it all goes back to looking at, it's describing what everybody observes. So typically in fluid mechanics, instead of using that form of the equation that we just derived for Blasius for shear stress, people like to relate shear stress, and again, shear stress is tau zero, shear stress on the plate, to a momentum concept. And remember, we just finished momentum rho QV, rho times the velocity squared. Rho Q is velocity times area. So rho AV squared, rho V squared is a momentum term. And so we're just saying that commonly what people would do when you're looking at shear stress in general is to relate shear stress to rho U squared. So in this case, what people would say in this momentum form of the shear stress equation is that the shear stress, tau zero, is equal to 1/2, here's your rho U squared, and C sub F is a shear stress coefficient. That's a lowercase c sub f. Unfortunately, I try to stay consistent with the nomenclature in your textbook. We have a capital C sub f we're also going to be using. So this is lowercase c sub f, and it's known as the shear stress coefficient. However, when we solve this equation for C sub f, we can also take the Blasius form of the shear stress equation at the plate itself. And then we would combine those two, and we can get the shear stress coefficient for the Blasius equation. And I'm going to be talking about using all these. Right now, we're just developing them. And if again, you turn to page 6 in your handout, if you go to the left-hand column, you'll see delta prime, the next column, REX less than 500,000. No entry there. Why? There is no laminar sublayer in the laminar zone. The next row of that handout, delta, right next to it, 5x over REX to the 1/2. Again, we showed that on an earlier slide. The next row, tau zero, 0.332 mu u over x REX to the 1/2. That's what you see on the slide. The next row, little c sub f, 0.664 over REF to the 1/2. So again, this sheet is your Rosetta Stone, ultimately. And we're going to be walking through it for all the different types of scenarios. Today, we're just talking laminar. Ultimately, you don't know what type of boundary layer you have. That's one of the first things you have to figure out. Once you know what you have, you know which set of equations to use. So we're trying to make this methodical. So we can calculate the shear stress coefficient. However, to take it one step further, you can integrate this shear stress over the entire plate surface area. And when you do that, what you get is the shear force due to friction. This is also colloquially known as the drag force. Okay? And we're going to be talking about drag next. So when we integrate the shear stress right at the plate boundary, all over the surface of the plate, we get the resistance. So we know this is the equation for the shear stress at the boundary, tau zero. We can put that into the equation, and quite honestly, all you have in there is REX over X that would stay in the integral. So you can get a direct solution for this. And again, this is all from the Blasius dimensionless velocity profile, which is only good for the laminar zone. When we do that integration, this is the equation we get. Think of pulling a flat plate through a fluid. This is the force you would need to pull that flat plate through the fluid. Same thing for an airline. And then ultimately that's converted to power. And now you know how much fuel you have. Now you know how to size the fuel tank. Now you know how to size the thrusters, everything. So in that equation, again, REL, since we integrated from the leading edge to the trailing edge, at the trailing edge, X is equal to L. What comes out of the integration is what you'll see REL, and REL is the boundary Reynolds number at the trailing edge, where X is equal to L. So it's no different really than REX, it's just at a very specific location. And B is the width. Since we had to integrate over the area, we're looking at basically, if we were looking at down on the top of this, this is the X direction. So this was the leading edge down here, and this is just the width of this thing, B. Into and out of the board, into and out of the screen, into and out of your paper. And again, if you look at how this was developed, again, people like to put shear stress and force in terms of momentum terms, rho u squared. And so in a momentum equation, this would be the momentum form of a shear force equation. And the only difference is now you see the area in there, and this capital CF is in there. This is the shear force coefficient CF, also known as the drag coefficient. But it's a drag coefficient because we're only considering frictional resistance. There's more to drag than just frictional resistance. So if we rearrange the equation above, what we can find is that this shear force coefficient, this drag coefficient, capital C sub F, is in terms of the shear force and the dimensionality. We have the Blasius equation, which is also the shear force equation. We can substitute the second into the first. And again, that gives us the drag force coefficient or the drag coefficient, which again, if you look at page 6, that's what you'll see in the second column for capital C sub F. This is where everything was developed. Are there any questions that have been popping up? Great. So up to now, this is what we've been describing. And up to now, we're only talking about this zone. After today, we'll dance into the other two zones. Today, I just want to focus on really understanding what we're doing here. If you can understand what we're doing in this zone, you can really understand everything else on page 6 and which equation to use. So again, we're just focusing on page 6, these first two columns. And I'm going to do an example with these first two columns. And then next class, we'll talk about these other two zones. So here's an example. What force is necessary to pull a flat plate, 1 meter in length, 0.5 meters wide, through water at 0.1 meters per second? What's the power required to do this? The plate is completely submerged. So for example, it's in water. Did I say it's in water? Yeah, it is. So let's say here's the water surface. And what you have is it's moving at 0.1 meters per second. So this is relative motion. Originally, we had the plate sitting still and the fluid moving by it. And if you are an observer moving with the plate, it appears that the plate is sitting still and the fluid is moving by it. So relative motion. And we need this force necessary to create this exact motion. So this is what it's after. And then once we get the force, we can get the power. Same way we were talking about power and momentum. That force and this velocity is creating shear stress on both sides of this plate. Some of the problems you have to recognize that only the bottom side of the plate is being submerged. For example, the bottom of a barge. So always be careful that you know what you're talking about or what they're asking for when they ask you about these shear stress problems. So we know we have water. I went to the back of my book and I looked up these water properties, the viscosity, the kinematic viscosity, and the density. And remember, nu is equal to mu over rho. So you can see how everything works together and that all the dimensions are consistent. The first thing you have to understand when you're looking at these classes of problems is, do you have laminar, transition, or turbulence? And this is the text that you saw in an earlier slide. We need to calculate the boundary Reynolds number to figure out which zone we're in. And the boundary Reynolds number, again, REX is UX over nu. So X is equal to 0 at the leading edge. Where is the boundary Reynolds number going to be the largest for this plate? Capital U doesn't change. Viscosity of the fluid doesn't change. At the trailing edge, whereas X is equal to L, right? Okay, so at the trailing edge, this is the boundary Reynolds number at the trailing edge. It's the free stream velocity times the length of this plate divided by the kinematic viscosity. Free stream velocity, 0.1 meters per second. The length is 1 meter, and the kinematic viscosity is 1.3 times 10 to the minus 6. Something's wrong. That can't be right. You've got, this should be 100,000. So you've got, oh, that's not, this is okay, it's okay. I saw that as 1, it's 1.3. The number's okay. Let's see if I can reset. This is okay. Okay. So because 76,920 is less than 500,000, you have a laminar boundary layer at the trailing edge. As you move back this way, as we just discussed, the Reynolds number keeps decreasing because X is decreasing. So over the entire plate, you have a laminar boundary layer. So we can use Blasius's theory and everything that we developed today. So for the shear force on the plate, this is the momentum form of the equation. This was the shear force coefficient, the drag coefficient. We can certainly use the Blasius equation, but again, this CF was developed from that. So the shear stress coefficient is 1.33 over boundary Reynolds number at the trailing edge. We just calculated that to be 76,920. So 76,920 to the 1/2 divided into 1.33 gives us a shear stress coefficient of 0.0048. And then everything else in this equation on the right-hand side, we know. So the shear force is 1/2. This is CF. This is the area of one side. And we multiply by two sides. This is our density, rho, and this is the velocity squared. It should be in parentheses. And so when we calculate that, we get a force of 0.024 newtons. Not a heck of a lot, but that's what it is. Any questions on that? Power, remember when we were talking about moving vanes? Power is force times velocity. So in this case, we have the velocity of the plate, which again, in a relativistic sense, this is the free stream velocity. And we have the force we just calculated of 0.024 Newton. The force times the velocity gives us a power in watts, 0.024 watts. That wasn't so bad, was it? So again, we need to recognize first in all of these classes of problems, what is the boundary Reynolds number? Once you know what that is, it tells you which column of the equations to use. We knew today we were spending on laminar. We knew we were going to be in that laminar zone. And just remember that the laminar zone the laminar zone is where we have the Reynolds number less than 500,000. In this problem, it was like we were working from like 76,000. Was it 920? 290? What was it? 920. 920. So really, this was our problem that we just worked. All laminar boundary layer, well within the laminar zone. Next time, we're going to talk about being in the transition or the turbulence zones. So again, you can put your pencils down. This is all spinach for the brain. But again, whether it's moving a particle in air, aeolian transport, like sandstones, have you heard of Chalubes? Big sandstorms that hit Arizona or any desert area. That's transport of a particle against its ability to resist the shear stress of the fluid. So, basically what we do is we compare what the fluid creates to what the particle can resist. So typically tau c, the resistance, is a function of the particle size. The larger the particle size, the more it can resist. And so we calculate tau 0, the fluid's ability to create shear stress on the bed. And if it doesn't exceed the ability to resist, the particle stays there. Same thing with a fish swimming. In natural streams, these are actual velocity profiles in streams. So each color is a zone of constant velocity. And this would be in a cross section that is, you have scales that are much spaced apart on the horizontal than the vertical. But this is basically a channel cross section. It looks almost rectangular. And this cross section on the bottom is kind of on a meander bend. And what you see is, again, these colors, again, there's zones of constant velocity and they're constant intervals apart. When the color ribbons get thinner and thinner, du dy is getting larger and larger. You're getting a big change in velocity over a small distance. So where would you expect erosion in a stream like this? Right down here. And that's where you do get erosion on stream beds on the outside base of a meander bed. And of course, there are all different ways to describe resistance to flow, but ultimately we can describe the resistance on the bottom of the channel using the same precepts that we developed here. And then ultimately we can start to look at how the shear stress relates to particle size. And these are actually what we use when we're looking at designing sediments. So let's say you wanted to design a riprap swale. You need to figure out which particle is going to be resisting the stream shear stress. So again, you can look through all of those. That's all spinach for the mind. I just threw that in there for you. Questions? All right, well, I covered what I wanted to cover for today. I would recommend that this is probably the last thing in your mind because it's not on Friday's exam, is it? But if and when you get back to looking at this, read this first, the handout, then read what's in the book, and it'll seem a lot more clearer. And then you can just move on with the homework problems. All right? No questions? Then for the second class in a row, I'm going to let you out early.